This is section 5.4. We are now going to cover exponential functions, both differentiation and integration. So as we have in several of the last sections, the first section, or the first part of this section, is essentially review of things that you know already, and then we're going to talk about how to differentiate and integrate the natural exponential function. And what I mean by natural is that we have e as the base. So e to the x, etc. is the function that we're looking at. You might have a little bit extra up here, but we're going to talk about just some of the properties, which should be properties you're familiar with, and then talk about how to use those in calculus. So we just finished learning about inverses, and we know that an inverse function simply undoes what the original function does. So when it comes to logarithmic functions, inverses can be found using the base of the logarithmic function and an exponential form. So before I talk about the definition of the exponential function, let's talk about what the natural exponential function is. If I have the equation e to the x equals y, which is my natural exponential function, using the properties of logarithms, and what I always call the swirly method, is we can call this log base e of y. And of course we never say log base e because log base e is natural log. Natural log of y equals x. So hopefully you remember that from way back when you first learned about logarithmic functions. Now we also know, if we're looking at an inverse, then we are going to simply replace x with y and y with x. So this is the inverse function for my natural log function, and you can see in my little picture over here, remember this is the line y equals x, that this guy is the natural log of x and this guy is the natural exponential function, and those are in fact inverses of one another. So essentially what we're saying is the natural exponential function looks like this and happens to be the inverse of the log function, or the log function. Natural log function is the inverse of the exponential function. So essentially what this means, dealing with inverses, is that if I have the natural log of e to the x, I end up with x, because we know if we are composing two inverse functions that we get x, and that e to the natural log of x is x. Now let's talk about this one first, just so we remember those properties of the natural log function. If I have the natural log of e to the x, there's a property that says I can move an exponent to the front. So this is x times the natural log of e. Well, the natural log of e is 1, so that's where I get the x from. If I look at the second one, I have e to the natural log of x. And again, because e and natural log, which is basically log base e, are inverses, they cancel out, and again it just leaves me with x. So why is this important? Because we're going to use that to solve logarithmic and exponential equations. So let's do a little throwback to when we first learned how to do this, just so we make sure we remember how to go from exponential, and notice these are not the natural exponential functions, this one is natural because e is the base, but it's the same process either way, to go from exponential to logarithmic. Essentially I'm saying that the base is always the base, so I start at the base and I say log base 7 of 5 equals x. So again, if I did the 6, it would be log base 6 of x equals 10. The important thing to remember is the base of my exponential function is the same as the base of my log function. This guy would be log base 4 of 6 equals x. Log base 10, and hopefully remember if it's log base 10, it's called a common log, so I don't have to write the 10, of 4 equals x. And this one would be log base e of 7 equals x, but of course we write log base e as natural log of 7 equals x. Now let's try going in reverse. So these are now log functions going into exponential form, and I'm still going to use that same method. Remember that the base, which is down here, is always the base, so 10 to the x equals 6, and notice I wrote in that 10 because it's a common log, and that's 10 to the x equals 6. So let's look at the others. Again, a common log, so this is 10 to the 15th equals x. 5 to the 12th equals x. 2 to the x equals 5. And remember, the base of a natural log function is e, so e to the 17th equals x. So let's do a little bit of practice finding the inverse. So again, when we find the inverse, we're going to replace x with y with x, and then we're going to solve to get y by itself. So I have the first one all worked out for us already. I have log of x equals y, and then I replaced y with x, and then I said, okay, I really want to get y by itself, so what if I said 10 to the x equals y? That's what I have here. Notice I wrote it y inverse because obviously it's the inverse of the function. So let's look at these others. Again, if you feel comfortable, you can press pause and do these on your own first. So first thing I'm going to do is to replace. So 5 to the y equals x. How am I going to rewrite this? Well, I'm going to rewrite it because it's exponential to start with. It's going to be a log function. So it's log base 5 of x equals y. And notice instead of y, I wrote y inverse. Let's do the same for this natural log function. So this is natural log. I'm going to replace x with y with x. Then I'm going to use that same method. The base is e, so e to the x equals y. So I wrote it y inverse equals e to the x. Last one, again, this is a natural exponential function. I'm going to replace x with y with x. Then I'm going to say log base e, which is natural log of x, equals y. And there is my final inverse. So let's work through the steps on how to actually solve an exponential equation. It's going to be a lot of the same things that we've just talked about. Keep in mind when I'm talking about solving, I'm saying I want x all by itself. So the first thing I'm going to do is I don't like the fact that x is an exponent because it's hard to work with it when it's up there. I'm trying to get rid of the exponent. So first I'm going to take the natural log of each side. So natural log of 7 equals natural log of e to the x plus 1. Now we have that property that says, hey, let's take this x plus 1, move it out front, and so essentially it's x plus 1 times the natural log of e, and then notice I didn't write natural log of e because we know that's 1 and it's not a part of our equation that we care about. Now I'm trying to get x by itself, so I'm going to subtract 1 from each side. This is my exact answer, and you should write that one first. Go ahead and write what this is as an exact solution, and then use your calculator to actually plug it in. So typically what I'm looking for is each of those solutions. So here's a question for you to try on your own. I would like you to try this question. When you're done, press play to see how you did. So the first thing I would do in this case is notice that I don't have the natural exponential equation or function by itself, so I don't have e to the 4x by itself, which means I want to start by dividing by 3. So dividing by 3 gives me e to the 4x equals 5. So now I have the natural exponential function on the left by itself, and I know in order to get that 4x to move out front, I'm essentially going to have to take the natural log of each side, because the natural log of e is going to give me just 1, and 4x is going to move, I guess I should do that one here, 4x is going to move out to the front of my equation. So that's what I have now is 4x equals natural log of 5. Obviously I'm solving for x, so I'm trying to now get rid of the 4, which gives me my precise solution, natural log of 5 over 4. If they then ask me for an approximate solution, I just get my calculator out. So here are my two solutions. So now let's do the same, but do this for a logarithmic equation. So again, we're trying to solve for x. X is stuck inside here. In order to solve that, I get the natural log function by itself, which it already is. Then I exponentiate each side, and what that means is I'm taking e to the exponent of everything I had there, and e to the exponent of everything I had there. Now, why do I do that? Again, because e and natural log are inverses, and they're going to cancel out, and that leaves me with just whatever the exponent was, which is 2x minus 3, equals e to the fifth. Again, I'm trying to get x by itself, so I'm going to add 3 to each side. That gives me 2x equals e to the fifth plus 3. I need to get x by itself, so I divide by 2. This is my precise answer, and then I plugged all of that into my calculator to get my approximate solution as well. Here's a logarithmic equation for you to solve. So press pause, solve the equation. When you're done, press play to see how you did. So this one, before I can exponentiate each side, I have to keep in mind that I have a 2 here. The 2 means that I'm going to use that property of logarithms to bring the 2 out front. So now I have 2 times the natural log of x plus 2 equals 10. Before I can exponentiate, I want that to just be the natural log. So I'm going to divide by 2 on each side. Natural log of x plus 2 equals 5. Now that I have natural log by itself, I'm going to exponentiate, which means I'm going to take e to the basically each expression. So e to the natural log of x plus 2 equals e to the fifth. E to the natural log essentially will cancel out, and I just get x plus 2 equals e to the fifth. I'm trying to get x by itself, so obviously I'm going to subtract 2 from each side. That is my precise answer, and then I plug it into the calculator to find an approximate solution. The last 2 slides of this part of the video are really just reminders. So remember that if I have the same base and 2 exponents, it doesn't matter if it's e or if it's x to the a times x to the b. Either way, I'm just going to add those exponents together, and if I divide, I'm going to subtract them. And the last one is just a reminder of the natural exponential function. So the domain is any value that we want to put in there, all real numbers. The range is essentially that you're not going to get a negative value, so 0 up to infinity. It's continuous, it's increasing, and it's 1 to 1, which of course means it has an inverse, and we already know that the inverse is the natural log function. It's concave down over its entire domain. As I go to the left, it approaches 0. Which we can see from our graph here, and as I go to the right, it approaches infinity.